Okay, in this video, let's look at number 7. Number 7 is also a set of connected objects. There's 3 blocks in the story. I noticed also, though, that there's 2 pulleys and the 2 of the blocks are hanging off the sides of the table. So remember that when there's a pulley, if they talk about the radius of the pulley or the mass of the pulley, then the pulley matters. And we know that T equals I alpha is going to come into the story somewhere, someplace. But in this problem, they're not talking about the pulleys at all. And so that's actually why I don't draw them. It just tells me that it's a pure dynamics problem, F equals ma problem, and I don't have to worry about the pulley. It's kind of like negligible in this particular problem. Okay, so we have 3 blocks. It says that there's the coefficient of friction between the block and the table is 0.5. So there's only going to be friction on this block. These blocks don't have friction. The masses are 3.75, 1.35, and 1.9 respectively there. All right, so I'm going to look at this picture here for a minute, and because this is the heavy block, I'm going to make a judgment call that this whole system is going to move in this direction. And obviously, if my guess is wrong, I'll end up with negative answers, meaning my answers are correct. We just had the direction wrong. So, but I think we're going to be okay with this. Okay, so if that's the case, if it's going this way, that tells me that friction is actually going to be going the opposite way. So we're going to start by finding the friction that exists here. And to find the friction equals mu times Fn, and this is Fw, this is Fn, and they're going to be equal because he's sitting on the table. So Fw would be 1.35 times 9.8, and that is 1323. So this Fn is 1323, and Fn times mu is 0.5. We find out that the friction in this problem is going to be 6.615 newtons going to the right. Okay, so letter A says determine the acceleration of each object, which means the acceleration of the system, and determine the tension in each of the strings. So I have 2 strings here. Let's call this string FT1, and we'll call this one FT2. And again, I can't find the tensions until I find the acceleration. So we will start with that, and we will find the acceleration by using F net equals m net times A. And I know it's m net because there's connected objects. There's more than one box in my story here. All right, F net. What is going to make this system move? I hope you can figure out it's going to be the FW of this guy. So let's take a second and find the FW. So 3.75 times 9.8 actually turns out to be 36.75 newtons. And 1.19 times 9.8, this actually turns out to be 18.62 newtons. So let's throw kilograms in for the other ones. Okay, so the weight of the heavy block is what makes the system move, and you're going to subtract off anything that you are dragging. So we don't really talk about the block that's sitting on the table, because a block sitting on the table isn't being dragged. If the table was frictionless, that would be absolutely nothing going on right there. But what we do drag is his friction. So 6.615, and we are dragging this because there's weight pulling down. And so again, a box sitting on the table isn't important in the story. His friction is important in the story, and a hanging down block is important in the story. So we pull with the 36.75. We have to subtract the friction. We got to subtract the hanging down block. And m net means we need to add the masses of each of those respective blocks up. And that turned out to be a perfect 7. And then we're going to solve for the acceleration of the system. and that turned out to be 1.645 meters per second squared. All right, and then to find the tension in the string, we just have to start someplace and draw a free body diagram. So I'm just going to start with this because it looks simple. All right, so I'm going to come down here and I'm going to draw that box. I'm going to turn it into a dot. And I see that this box has FW going, but I'm going to draw the FW arrow short because he's not really going this way. 18.62. I'm going to draw the string that's on him, and I'm going to label it FT2. I'm going to draw that longer because I expect this box is going up this way. And so now when I do F net equals MA, FT2 minus 18.62 equals M, that's the mass of that box, times A, whoops, I don't really have right to write that. I need to add in here 1.645, and then I can solve for FT2. And I got a 21.7 newtons. All right, so this is 21.7 newtons. All right, to find FT1, I could do the identical thing over here, but I would make the FW arrow longer because he would be going down. Or I could do the one in the middle. This one's actually a little bit more complicated, but I'm going to do that one, partly because it is more complicated. So I'm going to draw the box on the table. And on the box on the table, I see I have an FT2 going this way, so I'm going to draw an FT2 going that way. We know that answer, it's 21.7. I also see I have friction going that way, so I'm going to draw friction going that way, 6.617. You'll also notice that I'm kind of making a change now, and I'm drawing my friction along the ground. We're going to need to do that as we continue going forward here. And then I have this piece of string, FT1, going to the left, and because I expect this whole thing to be going to the left, I'm actually going to draw that one longer, FT1. And I'm going to do F net equals MA, and so I would have my FT1 minus what's working against me, 21.7 minus 6.615. The mass of this block is 1.35. The acceleration of the system, 1.645. And I can solve for FT1. And I did not do that. I will just look at the top, and it looks like it's about 30.5 or 30.6 newtons. Okay, hopefully that helps you with that one.